Welcome to lesson number 2. Our goal is to train a model that's able to classify handwritten digits in their proper class. To do so, we have to note that large data sets can be split into a training data set and a test set. The training data set consists of inputs, each input corresponding to some answer, some label, and it's what we use to train the model. The neural network sees and learns from this data, updates the weights and biases accordingly, in order to come up with a model. A model which eventually classifies the training data accurately. However, as you know, at first you start with some random model which runs on the training set and produces a result. Clearly the results aren't accurate. By comparing the prediction made on the following training images to their actual labels, clearly it misclassifies them. Based on the result of the comparison, we minimize the error, the cross-entropy value, by updating the parameters of the model, the weights and biases of connections between nodes in the neural network in the direction with the least error. As we minimize the error, it starts to classify more and more of our data correctly. By constantly updating the labels and the predictions, we can keep training the algorithm to better fit our training data, until eventually it starts to classify them with high accuracy. This is ideal. After training our model, due to an optimization algorithm that minimizes the training error, by comparing the labels with the predictions, it begins to classify our training data with pretty high accuracy. Okay, so using our training data, we trained our model. What happens if we now try to classify new data that it's never seen before? Right here is a test image. The difference between a test image and images in our training data is that the training images are what we use to train the neural network, update its parameters until the error is completely minimized. That way, when the neural network is introduced to new images that it's never seen before, it's able to classify them. Although, if we were to run this image through our neural network, clearly it misclassifies the test image. The problem being, the classifier, when it's introduced to new data that it's never seen before, it doesn't do a very good job. Why is that? Usually we're interested in how well the machine learning algorithm performs on data that it's never seen before, since this determines how well it will work when it's deployed in the real world. In our case, what happened was that our model itself was trained to fit our training data, but it wasn't generalized to classify new data that it's never seen before. That being said, we don't want our classifier to only perform well on data that it was trained on, but also on new, unseen inputs. The ability to correctly classify newly inputted data which don't have a label is known as generalization. When first training our machine learning model according to the training data, we aim to reduce the training error. However, we also require the test error, the generalization error, to be low as well. The problem with training classifiers when being trained is that they tend to memorize the training sets, and they do it considerably well. This classifier is memorizing what these images are, instead of training itself to look for patterns or general features. It's just memorizing them according to their labels. So if I were to introduce it to new images that it's never seen before, it wouldn't do a very good job, and that's totally expected. Say you're studying for a math test. It would be pointless to just memorize specific problem sets. Rather, you should understand and analyze the general concepts. In the case of our classifier, naturally it will try to memorize the training data, but by doing so, it fails to generalize to new examples. We don't want a complex model which perfectly fits the training data, since that's not going to generalize to how the model can be used in the real world. We only want the model to be complex enough to fit the data, and at the same time not cause problems on the test data. We're going to observe this trend once we implement all of this into code. But just notice that at some point in the graph, the more we minimize the training error, the bigger the test error. Keep that in mind. That being said, the test images, the test dataset is collected separately from the training images of the training datasets, and we use our test images to estimate the generalization error, and thus measure the performance of our model when deployed in the real world. Ultimately, what we want to do is ensure that the training error is small, and we also want the gap between the training error and the test error to be small as well. That is, we want our trained model to effectively generalize our test data. The first factor corresponds to a central challenge known as underfitting, whereas the second factor corresponds to a modeling error known as overfitting. I've previously mentioned these terms, underfitting and overfitting, but I've never really gone into a lot of depth. Let us first talk about underfitting. Underfitting occurs when your model isn't provided with sufficient capacity for it to be able to capture the data's underlying trend, and thus it's not able to actually fit the training sets. For example, generally image recognition is quite a complex task and requires a deep enough neural network that's able to develop a model that's flexible enough to correctly classify the training data. If I tried to use a single perceptron-based network with a simple linear model, generally this will result in an underfitting model. It just wouldn't have enough capacity to accurately fit the training data. Let's look at another regression type example, where we expect the capacity of the algorithm to be appropriate for the complexity of the task it needs to perform. In this example, let's compare a linear function of degree 1 and a quadratic function of degree 2, where each of them attempts to fit a problem whose underlying trend is quadratic. The linear function isn't able to pick up on the curvature, and thus isn't able to properly fit the training data, so it underfits. Whereas the more complex quadratic model of degree 2, the quadratic model perfectly matches the true structure of the task, and would be able to generalize new data with minimal error. In summary, models with insufficient capacity are unable to solve complex tasks. Models with high capacity are able to solve complex tasks, but if their capacity is too high, they may overfit, which introduces the concept of overfitting. For example, if I use a polynomial of degree 9, our data suffers from overfitting. It indeed exactly passes the training points, but doesn't extract the correct structure, and is thus not able to effectively generalize to new data. How do we know if a model becomes too overfit? Well, a good indication is when a model performs well on training data, achieving low errors, but performs much worse on data that it's being tested on. Generally speaking, the more hidden layers a node a neural network has, the more idiosyncratic, the more distinctive and peculiar features that it's able to catch and memorize. Looking at this image, if we overfit the network, what it's going to do, for example, is catch that the image has a white pixel on the bottom left corner. It memorizes very specific properties of the training sets, instead of coming up with a general pattern of what the number 3 should look like. That way it's able to identify other handwritten 3s, which generally would follow a similar pattern. You never want it to recognize specific features of our training data. That being said, how would we fix overfitting? Well, if a model is too overfitted, it could be that we need to reduce the depth and complexity of the network. It could be that we need a smaller number of nodes in each layer. It could be that we need to reduce the number of epochs in which our network is being trained on. so on and so forth. All of these are different methods that can help us reduce the capacity of our model. We still haven't mentioned validation sets. We'll get there soon, but to wrap up this video, we'll have a graph which plots the training error and the generalization error. At the very beginning, when using a model with insufficient capacity, when the function is way too simple and isn't able to capture the underlying trend of our data, both the training and generalization errors are very high, which makes sense. As we increase the capacity of our model, as we increase its complexity to properly fit the data, the training error decreases and asymptotes to the minimal possible error. At this point, we reach the optimal zone, where the function being used to fit our data isn't too simple so as to underfit it, but it's also not too complex so as to overfit our data. But it's simple enough that way the test error, the generalization, is quite low. In this optimal zone is the smallest gap between the training and the test error. From then on, as we keep increasing the complexity of the model to fit our training data, the training error accordingly keeps decreasing as it now starts to memorize very specific features of the training sets, classifying them to a maximal accuracy with low error, but it isn't able to generalize to newly inputted data, and as such the test error is high, and accordingly the gap between training and generalization error increases. Eventually, the size of the gap becomes so large that even though the training error is small, we are not able to generalize our model to fit new data, and thus we enter the overfitting stage, where the capacity is just way too large. This makes regularization a central concern in machine learning. In this course, we've learned about optimization algorithms like gradient descent, which aim to reduce the training error, whereas regularization techniques aim to reduce the generalization error. This is just as important, and we'll use regularization techniques later on in the course, but at the same time, this segues into our next discussion on validation sets. Let's talk about that in the next lesson.